Good morning students. Today is lecture 3 under module 3 and as you know that we are discussing about biorefinery and concepts under this module. So, today we will be discussing about the economics and the life cycle assessment of biorefineries. So, let us begin. The development of a new biorefinery, its design and construction requires huge investments. Cost estimations are often paramount for deciding the economic viability of biorefineries and must be performed on a case by case basis. However, it is possible to make a rough estimation based on data from demo plants, process modeling and or literature at various stages of the biorefinery development. A biorefinery system includes the harvesting, storage and transport of the products as well as the biorefinery itself. Innovative new conversion technologies usually follow a development pathway from the lab to piloting, then demonstration and finally, the construction of a commercial plant. The number of years for a bio-based product to reach commercialization that may depends heavily on the economics and hence on drop-in versus non-drop-in, which means existing demand and infrastructure, type of conversion technology and supply chain integration. Total cost can be divided into two things. One is a capital expenditures which is called as capex and then the other one is the operating expenditure which is called opex. Now, capex can be subdivided into mainly two things. One is plant cost and offsite cost and another cost also we can add on which is called engineering cost. So, the plant costs represent the capital necessary for the installed process equipment to with all the auxiliaries and accessories that are needed for the complete process operation. So, it including from the piping, instrumentation, installation, foundations, site preparation, everything. Whereas, off-site costs are not directly related to the process operation, they rather include costs of the addition of the site infrastructure, for example, power generation units, boilers, pipelines, offices, etc. OPEX consists of fixed and variable costs. Variable costs comprise cost of feedstock and supplies, waste management, product packaging, finished and semi-finished products in stock, etc. Fixed costs comprises salaries, taxes, license fees, interest payments, marketing cost, etc. So, this gives us a rough idea about what are the different types of costs involving a biorefinery. So, if you represent it in this in a schematic, so you can understand in a better way. Please have a look, you can see that 20 to 30% of the cost comes under the capital costs. So, which are investment costs basically the equity, interest rate, lifetime, etc. Then the major cost is 40 to 70% is the consumption related cost. So, these are feedstock cost, auxiliary like electricity requirement, energy basically, chemicals, disposal costs, etc. Then the next is 10 to 25% is the operation related cost. So, which takes into account the manpower cost, insurance cost of services, etc. So, all these things, these three are basically the cost of the entire biorefinery process. So, minus if you do the revenue, then that is because that will become your profit. So, estimations for the cost of biorefinery products are affected by a range of drivers that could change in direction and importance over time. So, some of these include are supply cost, market price and demand, competing non-energy markets for biomass, preferences of farmers and woodland owners, success of alternative waste recovery and recycling, production cost, storage cost, distribution cost, access to market. So, the first one supply cost is basically the feedstock supply cost. Okay. So, how the feedstock is getting procured from the source getting transported and all these things will come into that. Then again the market price of the feedstock and market price of the product that you are eventually going to sell off, all these things comes under that. Okay. With respect to demand of that demand for that particular product. Then the second is competing non-energy markets for the biomass. So, one of the most important thing that we need to understand at this point also that this biomass products acceptability has to be increased. So, public awareness and campaigning is required to do that. So, right now, even the when somebody is going to install a biorefinery, it is paramount important that they should also work on increasing the awareness of the bio-based products, right. Then preferences of farmers and woodlands. So, This is for that both that things, one is that feedstock procurement and all these things, then second that to whom you are selling the products. Okay. So, in both the cases farmers are of course as stakeholders and the woodland owners. Okay. The next one is about the success of alternative waste recovery and recycling. So, as I told you in one of our class that recycle and reuse is one of the most important factor that is associated with the so called biorefinery concept. So, unless until we are looking for a value based products from the waste that is getting generated from the biorefinery itself, okay, then we cannot have a sustainable economy. Okay. So, that needs to be done. For that you have to develop the process technologies also. Production cost is of course very important, that has to be taken care of. So, then storage cost also important cost. How do you are storage? You are going to store two things. First is that storing of the feedstocks, second is that storing of the finished products, and apart from that in between also storing of your this wastes and all, unless until they get recycled and converted and recycled. So, and then distribution cost and access to market. So, all these will impact the entire costing of the biorefinery system. So, main economic factors are capital cost, plant capacity, process technology, raw material cost and chemical costs. The major economic factor to consider for input cost of biodiesel production is the feedstock, which is about 75 to 80% of the total operating cost. This is for an example, that let us understand that if biodiesel is the prime product or the main product from a particular biorefinery, then what is the situation. So, other important costs are of course labor, methanol and catalyst, which must be added to the feedstock with respect to biodiesel. So, using an estimated process cost exclusive of feedstock cost $0.158 per liter for biodiesel production, and estimating a feedstock cost of $0.539 per liter for refined soy oil, and overall cost of $0.70 per liter for the production of soy based biodiesel was estimated. So, I have given the reference at the bottom, you can refer to it later on. So, palm oil is the main option that is traded internationally and with potential for import in the short term basis. So, the oil in vegetable seeds is converted into biodiesel through oil extraction, oil refining and transesterification. And as I told you in last class, even last to last class, we have discussed that extraction technology should be developed in such a way that they are very efficient as well as they are low cost. And the cost of biodiesel can be lowered by increasing feedstock yields, developing novel technologies and increasing economic return on glycerol. Please understand that glycerol is one of the most important byproduct from the transesterification reaction or biodiesel production. Glycerol is a very high value product, but the problem right now is that the amount of glycerol that is produced across the globe and that is converted into useful products, there is a disparity. So, we have huge surplus of glycerol. So, unless until we develop technologies to convert glycerin to other value added products rather than what is right now being used commercially, then the sustainability of a biodiesel based biorefinery is still an question. Okay. So, let us look at a biomass cost, which is one of the most significant cost associated with the biorefinery. The biological fraction from waste generated in developing countries is 50% higher when compared with developed nations. So, waste based biorefineries play a vital role in the economy of developing countries. In India, the most common feedstock for bioethanol biorefineries is molasses, because there is a huge byproduct that is coming from the sugar processing industries, mostly based on our sugarcane. So, the market price of molasses fluctuated from 18 to 92 US dollar per ton in the last decade, and market price fluctuated between US dollar per ton for rice straw is between 11 to 13, bagasse 12 to 14 and rice husk is 22 to 30. Now, in India, food grain straw is mainly used as a cattle feed, followed by its used in industry as a packaging material, construction material, straw board and paper and hardboard units. Cost of agricultural and forestry residue is dependent on various parameters such as biomass production, pre-processing, handling and transportation. So, when we talk about a biomass cost, all these costs are coming into picture. Cost of residues fluctuated between 14 to 34 US dollar per ton minimum being for the bajra straw and the maximum for the arhar stalks. In another scenario, when the travel distance was 100 km from the farms, cost fluctuated from 36 to 55 per ton US dollar for bajra straw and arhar stalks respectively, highlighting the influence of transportation on market price of the residues. We have discussed about this travel cost in one of our lectures previously, that the transportation cost is a significant cost with respect to the biomass procurement cost. Okay. The cost of the biomass as it is will be very low, because anyway when it is getting procured from forest resources, agricultural field or anywhere municipal waste also, its price or cost is very less. But when we keep on transporting it, the transportation cost increases significantly due to two things. First, and where is the plant located, how far it is from the source, that is a source of procurement, and what is the density and shape and size of this biomasses. If it is low dense, then you need to, it is basically very high volume. So, transportation becomes difficult. Okay. Basically difficult as well as it becomes costly. So, India is known for its biomass diversity, which can be categorized as grasses, woody plants, fruits, vegetables, manures, aquatic plants and what not. There are so many. So, biodiesel manufacturers have also started using algae as a feedstock. These available biomass sources can be broadly divided into three categories: energy crops, agricultural crop residues, municipal and industrial waste, and we have already discussed this significantly in a few of our classes. So, let us now understand what contributes to the logistic cost. So, one of the bottlenecks involved in commercialization of biorefinery is the cost involved in logistics, which include several discrete processes: harvesting and collection of biomass on site, that is from the cultivation field or forest. Storage of biomass is a significant cost. So, proper storage of biomass is of paramount importance to ensure that round the year availability, even though they are harvested at a different time of the year, because most of the crops are seasonal. So, location of the storage space can be at the collection site, biorefinery or at any place in between the two sites. So, that is the location will eventually decide about the transportation cost. Then biomass storage at the collection site is a low cost option, but that is not always a win-win situation, because there are certain disadvantages associated with it, such as the loss of biomass material due to degradation, uncontrolled moisture content of biomass leading to processing difficulties, chances of contamination due to spore formation or fungal infection, and finally, low storage period as the farmers need the land for cultivation of next crop. So, biomass storage is a critical stage in the biomass supply chain, hence the location and facility should be decided based on the holistic analysis of respective storage units. Processing of biomass. So, low energy content of biomass in comparison to fossil fuels coupled with low density means that comparatively large amount of biomass is required to obtain a similar amount of energy. So, this poses a severe handling and transportation problems. Compacting of biomass through several processing or pretreatment steps is advantageous, as it reduces the volume of biomass as well as improves the storage, handling and transportation efficiency. The densification techniques, we have discussed that how you densify this. Okay. You make into briquettes, pellets and all these things. So, through densification techniques, the harvested biomass can be processed into bales, pellets, cubes, pucks, briquettes and wood chips. Technically, processing can be undertaken at any stage. However, the advantages are maximized if it is done after harvesting or collection stage. Transfer of biomass from the collection point to a common point from where the transportation can be initiated is also very important. It also involves loading of biomass into the transportation vehicles and unloading them once the biomass reaches the biorefinery. So, each and every step there is a cost associated. Transportation. Biomass feedstocks have geographically varied locations, low energy content and density, which makes transportation cost intensive step of the entire supply chain. So, cost input during transportation is dependent on travel distance, travel time and biomass density. Travel distance affects the cost involved in the fuel purchased for vehicles and also the travel time involved. Then travel time in turn affects the cost involved in hiring manpower, maintenance of the vehicles and insurance. Manpower is required for basically loading and unloading the biomass in the transportation vehicles. So, travel time includes the time spent on a round trip and the waiting time during the loading and unloading of biomass at the site and biorefinery respectively. Hence, the larger the distance between the two sites, larger the travel time and higher is the capital allocation toward manpower and maintenance. So, these things needs to be optimized. Another factor affecting the transportation cost is the biomass density. The low density of biomass means a large volume of biomass needed to be transported, hence more number of vehicles required or multiple trips to be undertaken by a limited number of vehicles. Economic viability of biorefinery system. So, economic viability of biorefinery systems, we will see a case study of bioethanol. Bioethanol plants and sugarcane mills are well established processes where the biorefinery concept can be implemented little easily, since sugarcane bagasse is a feasible feedstock to produce fuels as well as certain chemicals. Techno-economical analysis of ethanol production using mild liquefaction of bagasse plus simultaneous saccharification and co-fermentation shows a minimum selling price between 50.38 and 62.72 US cents per liter, which is comparable with the market price. The production of xylitol, citric acid and glutamic acid from sugarcane lignocellulose, that includes bagasse and harvesting residues, each in combination with electricity have been evaluated. The 3 biorefinery systems were simulated to be annexed to an existing sugar mill in South Africa, and the case study is there. Please read, the references has been given at the bottom. You can please refer to those and read in little details from these 2 manuscripts. So, the production of xylitol and glutamic acid has shown economic feasibility with an internal rate of return of almost 12.3% and 31.5%, exceeding the internal rate of return of the base case, which is 10.3%. Likewise, the production of ethanol, lactic acid and or methanol and ethanol lactic acid from sugarcane bagasse have been studied. Lactic acid demonstrated to be economically attractive by showing the greatest net present value. Almost it ranged from 476 to 1276 million dollars. So, in the same way, the production of ethanol and lactic acid as co-product was found to be a favorable scenario, since this acid has applications in pharmaceutical, cosmetic, chemical and food industry. So, let us now understand the biodiesel. So, as for biodiesel production, this industry also has the potential to integrate biorefinery systems to convert residual biomasses and wastes into biofuel, heat, electricity and bio-based green products. Glycerol is the main co-product in biodiesel production and can be transferred into valuable products through chemo-catalytic technologies. The valorization of glycerol for the production of lactic acid, acrylic acid, allyl alcohol, propandiols and glycerol carbonate has been evaluated. All glycerol valorization routes shown to be profitable, being the most attractive the manufacturer of glycerol carbonate. Palm empty fruit branches are an abundant lignocellulosic residues from the palm oil biodiesel industry. The conversion of this residue into ethanol, heat and power and cattle feed were evaluated according to the techno-economical principles. So, the economic feasibility of bio-oil production from the EFB via fast pyrolysis using a fluidized bed technology was studied. Crude bio-oil can potentially be produced from the EFB at a product value of $0.7 per kg with a payback period and return on investment of 3.2 years and 21.9% respectively, which is considered as almost a moderate range. Okay. So, the integration of microalgae and jatropha as viable route for the production of biofuels and biochemicals has also been analyzed in the United Arab Emirates context. 3 scenarios were examined in all of them. So, biodiesel and glycerol is produced. In the first scenario, biogas and organic fertilizer is produced by anaerobic fermentation of jatropha fruit cake and seed cake. And in the second scenario, production of lipids from jatropha and microalgae to produce biodiesel was evaluated, and the production of animal feed, biogas and organic fertilizer was also integrated. In the third scenario, that involves the production of lipids from microalgae for the production of biodiesel as well as hydrogen and animal feed as final product from the lipid extracted algae basically. So, this is the first scenario which was almost profitable compared to other scenarios. So, now we will understand about the life cycle assessment. Now, whenever we are going to develop a process technology or let us say refinery, biorefinery or any industry, whether it is a mass based industry or any other feedstock based industry, we need to carry out a life cycle assessment plus the techno-economical evaluation. So, we have discussed about the cost. In a nutshell, we understand what are the different types of costs that are associated in setting up a biorefinery. Now, we will try to understand what is the meaning of a life cycle assessment. So, LCA provides a quantitative estimation of the potential environmental problems of an examined system in terms of environmental indicators, proposing concurrently ways to overcome the environmental burdens, thus addressing thoroughly the issue of sustainability. The LCA results could provide the basis for decision to support establishing new technologies, processes or products for industrial applications and policy making for mitigation of climate change or fossil resource dependency. Based on the biorefinery system, the assessment of parameters related to its implementation potentials as for example, feedstock availability, then feasibility and stability add valuable aspects of the new products and production technologies. Moreover, these results constitute the cornerstone of robust conclusions and future oriented recommendations for the industries. So, let us understand how it happens actually. So, in a step 1, we have to define the goals. Okay. So, in the step 2, we will talk about the inventory data collection. In step 3, it is the impacts assessment, and in step 4, it is the results interpretation. So, the method of choice for deriving environmental indicators for biorefinery is life cycle assessment based on the ISO 14040 methodology encompassing the 4 steps as mentioned here. So, if all necessary input and output streams cannot be collected within the framework of the life cycle inventory due to a lack of valid data, so this can result in a retroactive redefinition of the system boundaries. The sensitivity analysis can also show the necessity to refine the system boundaries. So, in the when you define the goal in the step 1, basically you are talking about the system boundaries. You define the system boundaries, okay, functional units and what are the environmental impacts that is going to arise from the processing of the feedstocks, okay, handling them and when you product and convert them to value added products. In the second step, it is about inventory data collection, where experimental and literature data will be collected and stored, then databases will be accessed and you have to take this one the help of certain LCA softwares. In the third step, it is impact assessment, where the data processing for the environmental impact will be basically carried out to understand whether is there any environmental effect at all from the biorefinery perspective when you are processing the biomass to and converting to the value added products. And in the final step, that is the result interpretation. Here you basically elaborate what are the results we have received, we have actually got, and then based on that what are the recommendations for reducing the environmental impact and or mitigation. So, these are the essential 4 steps which are required to carry out the basic LCA study. There are so many other things also, but in a nutshell let us try to understand what is LCA. Okay. So, in the course of evaluation and interpretation, it can be determined that additional data must be generated in order to arrive at representative results. Therefore, the data required for the life cycle inventory is of particular importance within the LCA. The representativeness of data and factors needs to be verified in a case specific way for every biorefinery pathway assessment. The life cycle steps are implemented in different modules of the assessment from the feedstock generation to the standardized products. Furthermore, the modules gather the inputs consumption and calculate the emissions of the 3 main greenhouse gases: carbon dioxide, methane and nitrous oxide, and primary energy demand. So, the parameters that are considered for each production step of the biorefinery as input factors for the assessment are agro inputs, field work, field emissions, use of the fossil energy resources, conversion inputs, transport efficiencies, emissions from steam production, electricity production, multi-product outputs and the residues. So, there are 2 categories of input parameters: emission driving parameters and process parameters. As for example, the input of the field emissions needs the process parameter of the field work to calculate the exact amount of emissions. So, you have to basically collect so much of field data and then analyze them to understand the value of emission. The emission driving parameters are linked to emission coefficients. Applying representative emission factors is a significant challenge, and the application of default values and non-specific data, as for example, on energy mixes, can impose strong divergences concerning the representatives of results. The use and disposal phase can only be covered partly, as operators and developers have only limited data and influence on the use and disposal of products. Based on these limitations, the results can only be interpreted as estimates. Further, the overall emissions of the different biorefinery operations and process steps can be calculated, and in a second step the emissions are converted to a specific value with regard to the functional units, like for example, the annual products quantity. The handling of cutoff rules must also be very carefully considered, as this leads to considerable uncertainties in the result if too many material and energy flows are excluded from the LCA. So, non-relevant life cycle stages, including the associated material and energy flows, are excluded based on these cutoff rules. Cutoff criteria should ensure that this procedure is not purely arbitrary. Life cycle thinking is referring to a maximum balancing scope, as for example, cradle to grave. So, the meaning of cradle to grave here is basically you start from the feedstock and end up in the finished good or finished product, the entire life cycle. So, that is basically from cradle to grave. What does it mean? Okay. As a bio-based product strongly reveal their positive environmental potential, especially in the use phase by substituting fossil based reference products and services, or end of life phase related to the biogenic origin of product bound carbon. So, let us look at this particular generalized system boundaries of a biorefinery LCA approach. So, this is a complete system boundary that is defined for a particular value added biofuels based biorefinery. So, you start with the biomass production chain, basically inputs, energy, fertilizer, etc., to grow biomass, procure, transport, process. Then in that case there will be emissions and there will be residues. Now, to make a sustainable biorefineries, we also should convert these residues into value added products. That is basically the recycling of the wastes. Then the biomass goes to the processing unit, the plant in which you are processing into value added products. So, when you are doing that, there is enormous amount of emissions that is coming out, right. And of course, again another set of bioproducts. That bioproducts also should be taken into consideration to convert and to value added products, and basically minimize the waste and recycle them. Inputs are energy, chemicals, nutrients, enzymes, and there may be many things, and the biofuels and other value added products in terms of energy, electricity, then your platform chemicals. Okay. So, this is the complete system boundary and it is the entire system. Now, I can take a small boundaries here also, here one, I can have a boundary here, I can have a boundary here. So, this is a generalized one, right. So, I can take one processes, one system boundaries, find out what are the emissions, and also we can take care of the this one, do the techno-economical assessment also by defining the system boundaries. So, this is how it actually the boundary has been defined for a biorefinery approach, LCA approach. So, let us now understand the current challenges of assessing biorefineries. So, considering life cycle assessment as an established method to assess the environmental impacts of a product based on the ISO 10400 criteria, the choice of allocation is one of the most discussed issues. Additionally, the choice of functional unit, system boundaries, and whether the LCA is accounting or consequential are the key issues for the LCAs of biorefineries. So, functional unit and allocation, let us understand what it means. So, the functional unit is often reflected by reference material flows, as for example, the amount of output rather than the function, as for example, the heat value. Biorefineries producing multiple outputs increases the difficulty of identifying one main function. The importance of the choice of functional unit for comparing and interpret results is unquestionable. The multifunctionality of biorefinery concepts are also leading to the common challenge of allocating the environmental impacts to various outputs. So, different outputs from biorefinery can actually have different functional units and physical attributes, leading to a core question in the LCA for biorefineries. The partitioning method is an ideal choice for biorefinery which is based on artificial splitting up of multifunctional processes into a number of independently operating monofunctional processes. So, it is easier to assess basically if you do like that. So, it is necessary to distinguish between processes with or without an underlying physical relationship between the outputs and the emissions. Now, let us understand system boundaries. So, the choice of system boundaries or balancing the scope strongly influences the result of value based biorefinery quality evaluation. So, you can go for an entire cradle to grave life cycle. However, from a practical point of view, due to limitations in data availability, especially in terms of the use and the end life phase, the assessments often follow a cradle to get or get to get approach. So, these are mid segment approaches. Okay. The considered life cycle stages include biomass cultivation, process steps upstream and inside the biorefinery, consumer use of biorefinery products and product disposal. Although there is a distinction between bio-based and non-bio-based value chains, it is worth noting that a purely bio-based value chain may have connections and interactions in common with non-bio-based value chains. The system boundaries of the case studies in the reports are mostly cradle to get. The use and disposal phase is often not covered as operators, and developers of biorefineries have only limited data and influence on the use and disposal of products. So, this is an interesting slide where we can understand what is this cradle to grave, cradle to get and get to get system boundaries basically under a LCA concept. Look at the cradle to grave. So, it starts from the biomass cultivation and extraction, everything to recycling and disposal. Do you get it? So, it is the entire biorefinery system. Okay. Now, let us understand what is cradle to get, which is intermediate boundary. So, it starts from biomass cultivation and extraction. Let us go to the production, processing, intermediate product, and let us say till product production or processing. It is not sacrosanctly defined like this. You can either take it that side or you can bring it this side also. You can end anywhere, right. It depends upon what type of data is available basically with you, and you can how easily you can proceed with the availability of the data basically. Then if you understand about get to get, it is basically a single process. Let us see this production and processing of the biomass. Okay. This is one get to get approach. It can be production and processing of the intermediate product. Okay. Again get to get approach. So, this is how the system boundaries has been defined for a LCA analysis. Okay. So, the second one is a non-bio-based value chain and top one is the bio-based value chain. Okay. So, now let us take a case study of the technical, economical and environmental assessment of a biorefinery. So, we are talking about a two platform biorefinery where there is a C5 and C6 sugars platform basically to convert it to bioethanol and the biomass is corn stubble. So, the raw material is corn stubble, the platform is the sugar platform, both C5 and C6. The processes is a lignocellulosic biomass conversion. The product and the end material, the major end material is ethanol, there may be other byproducts also. Product energy is electricity and heat. Concept according to the VDI 63010 is the lignocellulosic biorefinery and the balancing scope is cradle to get. So, this case study is characterizing a lignocellulosic biorefinery using residual corn stubble to produce ethanol as fossil fuel substitute. So, it has on-site process energy generation via lignin combustion in a boiler and electricity production with steam from combustor. So, the inherent meaning of this particular sentence is that whatever lignin is getting generated during the pre-treatment or delignification of the biomass is getting burnt to produce electricity basically. Additionally, biogas is generated on site by the anaerobic digestion of wastewater. No external energy supply is needed. Every energy that is required for the biorefinery is getting generated on site. So, the lignocellulosic biorefinery has on site cellulose enzyme production facility also. So, the biorefinery process described is designed for a capacity of approximately 104 ton corn stubble operating 24 hours 6 days a week. Now, this corresponds to approximately 7,500 plant operating hours per annum. So, this is the overview of the techno-economical assessment and the process pathways of the ethanol synthesis from corn turnover. So, these are the agrochemicals requirement. how much it is required, it is written there. The energy, how much it is getting consumed in the form of electricity, steam, and how much electricity credit you are generating basically. Then the operating materials like cost of the here that say the corn strip liquor, sulfuric acid, diammonium phosphate, some other solvents, all these things, and of course, the water, it is a huge requirement and a huge cost. Okay. So, then it goes to the cultivation of the corn stubble, you get some, let us say 3883 kilograms per hectare per year. Then it goes to the lignocellulosic biorefinery, this is the biomass productivity, comes to the biorefinery, and you get almost 834 kilograms per hectare per year of the ethanol. Then of course, there are other things. So, you can refer it and get an understanding that how the TE looks like. Okay. So, then lignocellulosic ethanol biorefinery pathway. So, ethanol is produced based on corn stubble. The milled corn stubble is pretreated in a dilute acid pretreatment process. So, 18 milligram of sulfuric acid per gram of dry mass is the optimized requirement. Enzymatic hydrolysis is used to convert the hemicellulose and cellulose into monomeric C5 and C6 sugars and lignin, which are the platform inside the described ethanol biorefinery. Cellulose is produced on site. The C5 and C6 sugars are fed into fermentation tanks. The fermentation uses metabolically engineered strains of the Saccharomyces cerevisiae microorganisms that are capable of co-fermenting xylose and glucose to ethanol. So, this particular Saccharomyces cerevisiae which is a engineered strain, okay, it can co-ferment both C5 and C6 sugars to ethanol, whereas a separate hydrolysis and fermentation process is applied, SHF process. So, finally, the fermentation broth is fed into a distillation process. Distillation columns and molecular sieves are used to produce 99.5% ethanol. Okay, it is a very great purity. So, again you can see here whatever lignin is coming from this hydrolysis after the delignification step is being fed to the boiler. So, lignin is burnt basically, you generate electricity and heat, okay, in a CHP platform. Okay. So, this is the biorefinery and reference system, a value chain case study with reference to cradle to gate approach. So, the biomass, corn stubble, transport, biorefinery, we get ethanol, lignin converted to energy, whatever left out can be converted to fertilizer. Okay. It is not the fertilizer is the only thing, it can be any other things also. Okay. So, crude oil, extraction, transport, refinery, gasoline, naphtha, aromatics, etc. So, this is your general refinery, this is a biorefinery. So, the key characteristics of the case study based on the two platforms C5, C6 sugars and lignin biorefinery to produce bioethanol, electricity and heat from corn stubble is that. So, the state of technology is almost commercial, okay. Country is United States, the main data source is from literature. Okay. The products are ethanol and electricity, these are the costs given in million, this one actually euro, investment, feedstock, operating, labor and all these costs, and then auxiliaries, feedstock, conversion rates are also given. Okay. So, if you look at the mass balance case study, so you can see these are the different things, wastewater, conversion loss, lignin converted to CHP basically, ethanol, water, corn stubble, chemicals. Have a look at here the input. The major input cost is of course that of the water, followed by the biomass, that is the corn stubble, and the small amount is due to the chemicals. Now, if you talk about the output, okay, so the major cost is wastewater. Okay. So, now this was what I was mentioning, that wastewater need to be treated, okay, recycle basically in house, so that our dependency of fresh water will come down. Followed by the conversion losses, huge amount of conversion that is getting lost, and then this yellow one you can see that is the lignin. Of course, it is value added because it is getting converted to electricity and heat, followed by this brown one which is the ethanol production. See the cost in terms of the mass balance basically. Okay. So, when you talk about the sharing of the cost, it is again in the same manner. Okay. Raw material supplied, followed by this one here auxiliary and operating material, followed by the imputed interest, then that next is the write off cost, and there are some other costs like insurance and auxiliary and operating material. So, if you look at this sensitivity analysis of the cost structure in a case study, you can see this the red one is the raw material supply, okay. and the blue one is the total investment, okay, the entire investment cost, okay, and the line which is horizontal you can see that is the others cost. So, based on the self sustained energy supply within the biorefinery, okay, especially no effect on the sensitivity of the overall cost structure is related to the energy cost. So, that is what is the understanding from this particular slide. So, value chain environmental assessment in case study. So, this is an overview of the TE assessment results case study. So, the greenhouse gas emissions, this was estimated after the your LCA study, okay, or TE study. Raw material sourcing cost over is almost 2651 tons of carbon dioxide equivalent. So, the biorefinery 35,100 reference system 368,751 tons and savings is 331,083 tons. So, then this is the cumulated energy demand in terms of the terajoule, then this is the costs, okay, in terms of the million euros. If we talk about the greenhouse gas emissions of biorefinery compared to reference case study, you see this is the second generation ethanol biorefinery, okay, right, and this is the greenhouse gas emission. You see the gas, it is nothing when you compare to the fossil reference. So, this is quite understood from this particular slide is that when you talk about a biorefinery concept, that greenhouse gas emissions is far less compared to the fossil fuel emissions. So, the next is cumulative energy demand of biorefinery compared to reference. So, again you can see that the energy demand for biorefinery, okay, with comparison when you compare to the fossil fuel reference with respect to renewable, it is little higher. But then you have to understand what is the output in terms of every aspect including the environmental aspect. It is not about only the energy demand or energy requirement. So, this is the cost and revenues, the final one you can see this is the input cost basically, okay, and this is the final value of the ethanol selling price. So, you can see that it is marginally higher than that all the input cost and everything is been accounted here, whether it is water supply, disposal, raw material, insurance, maintenance, everything. So, still we can understand from this particular slide that the ethanol cost, the annual selling price of the total amount that is produced is higher than the input cost, okay, or the production cost. So, that means we are in profit, okay. So, let us conclude this LCA discussion. So, today's biorefinery processes still show significant optimization potential, while the production processes of fossil based products are technically mature and optimized. Technical developments in the biorefinery sector continue to generate new knowledge, and as they are commercialized and deployed, these are likely to lead to further improvements by economies of scale. As a result, it is expected that the production cost for biorefinery products will decline in the near future and that the products will become more competitive over time. Until this is achieved, biorefinery pathways will continue to rely on targeted policy measures and public transport programs to drive the development. The wide implementation of biorefinery technologies requires that a large number of possible products meet the quality and price requirements in the market. So, basically price is one factor, another is the awareness of the bio-based products and their acceptability by the end users. So, in addition, it is necessary to identify and optimize the site adapted biorefinery technologies and recycling paths from the multitude of potentially available raw materials and conversion paths. So, with this I wind up today's lecture. In case you have any query, please feel free to write to me at kmohanty@iitg.ac.in or post your query in the SWAYAM portal itself. I'll definitely answer those. In the next module, we will be discussing about the biomass pretreatment technologies. What are the different types of biomass pretreatment techniques that is available, what are their pros and cons and how they can be carried out. Okay. So, thank you very much.